Welcome to another edition of The Explainer. Today, we are uncovering the hidden physics behind literally everything we hear. I mean, from a tiny whisper to a roaring jet engine, the mechanics making it happen are actually surprisingly similar. So, let's just dive right in. Let's start things off with a super simple question. Just picture your favorite live acoustic performance. When a musician strums the strings of their guitar, how does that event, happening way over there on the stage, actually physically bridge the gap of empty space to reach your ear? It feels instantaneous, right? Almost like magic. But as we're going to see, it's actually a highly structured mechanical relay race. Take a look at the sheer blur of motion in these strings. When a string gets plucked, it doesn't just move once, it rapidly shakes back and forth. And this establishes our absolute foundational rule for today. All sound is born from physical vibration. Without this rapid back and forth movement, the universe is just entirely silent. Here's the roadmap for our journey today. First, the birth of sound. Second, how sound waves travel. Third, the silent vacuum. Fourth, decoding loudness and pitch. And finally, measuring sound's speed. All right, let's start with part one, the birth of sound and where it all begins. Check out this snare drum. When that drumstick strikes the drumhead, it applies a downward force. But because the drumhead is elastic, it snaps right back. It overshoots its original position, goes up, goes down, and physically moves back and forth. It is literally vibrating the surface of the instrument. But remember, that surface isn't alone in the world. It is completely surrounded by an ocean of invisible air. So here is the crucial chain reaction. The object vibrates. When it moves outward, it physically smashes into the air particles hovering right next to it. Those particles are displaced, basically getting knocked out of their resting positions. And this initial displacement, that's the spark. From that single microscopic collision, sound waves are officially formed. Moving on to part two, how sound waves travel, moving through the air. Now, to understand the travel, we've got to understand the vehicle. Sound travels as a longitudinal wave. As you can see defined here, it's a mechanical wave, which just means it absolutely requires a physical medium to travel through, like air, water, or even solid steel. And the key word here is longitudinal. That means the particles vibrate back and forth in the exact same direction the wave itself is traveling. So they aren't doing the wave like fans in a sports stadium going up and down. No, they're pushing forward and backward. And this brilliantly illustrates that exact concept. Just look at the pattern of these particles flowing from the speaker on the left to the ear on the right. You'll notice they aren't evenly spaced at all. The vibrating speaker cone pushes forward, squeezing the particles tightly together into these dense bands. We call those compressions. Then, as the speaker cone pulls back, it creates this area of low pressure, and the particles spread far apart into what we call rarefactions. This repeating pattern of compressions and rarefactions bumping into each other down the line, that is exactly what a sound wave looks like moving through the air. Which brings us to part three, the silent vacuum, and why space is quiet. Let's contrast two entirely different environments for a second. Down here on Earth, we are constantly swimming in a thick soup of air molecules. These vibrating particles act as our medium. But if you look at the vacuum of space, matter is incredibly sparse out there. Between planets and stars, it's effectively empty. And because sound is a mechanical wave, well, if there are no particles to get displaced, there is no chain reaction. There is simply no wave. And we can actually prove this right here on Earth with the classic bell jar experiment. Watch what happens across these three stages. In the first jar, you've got an electronic bell ringing inside and there's air present. You can easily hear the sound. In the second jar, a vacuum pump is turned on, gradually sucking the air out. As that particle density drops, the sound becomes noticeably fainter. Finally, in the third jar, an almost total vacuum is achieved. Now, the bell is still physically striking the metal. It's vibrating fiercely inside there, but because there is literally no air inside the jar to catch the vibration, absolutely no sound is heard. It is pure, undeniable visual proof that you have to have a medium. All right, part four, decoding loudness and pitch, the flavor of sound. Let's see how this builds our understanding of what we actually hear. Notice the stark contrast between these two sets of graphs. On the left, we're looking at loudness. You see the word amplitude. Amplitude is the height, or basically the strength of the wave. A small, shallow wave gives you a quiet sound, but a massively tall wave with high amplitude, that gives you a booming, loud sound. Now look over to the right. This is about pitch. Over here, the height doesn't matter at all. It's all about how tightly packed the waves are. Stretched out waves give you a low pitch, like a deep, rumbling voice. Tightly squeezed waves give you a high pitch, like a sharp whistle.
To measure that tightness accurately, scientists use the term frequency. It is strictly defined as the number of sound waves that pass a fixed point in exactly 1 second. So if your wave has a high frequency, it means lots and lots of waves are hitting your eardrum every single second, and your brain perfectly translates that rapid-fire impact into a high-pitched sound.
And finally, part 5, measuring sound's speed, catching the wave. So, at a standard room temperature of about 20 degrees Celsius, sound travels through the air at roughly 344 meters per second. That is incredibly fast. We're talking around 770 miles per hour. But think about this for a second. Centuries ago, way before we had modern computers and precise lasers, how did humans actually manage to measure the speed of an invisible force moving that fast?
Well, they used brilliant, structured observation, famously documented as the pistol experiment. Here's how it worked. You take two people and separate them by a large distance, say well over 100 meters. One person fires a pistol with a sharp, distinct sound. The observer, holding a stopwatch, doesn't wait to hear the gun. Because light travels so much faster than sound, the observer starts the stopwatch the exact moment they see the flash or the smoke of the pistol. Then, they just wait. A fraction of a second later, the physical sound wave finally hits them, and they immediately stop the watch. By dividing the known distance between the two people by the time on the stopwatch, humans calculated the speed of sound. Pretty genius, right?
And today, we use this exact same math to perform incredible feats, like measuring the depth of the ocean using sound, a process you probably know as sonar. Take a look at the math on this table. A boat sends a sound pulse down, and an echo returns exactly 2 seconds later. If we know sound travels through water at roughly 1,500 meters per second, multiplying 1,500 by 2 seconds gives us a total distance of 3,000 meters. But you've got to remember one absolutely crucial step here. That 3,000 meters is a round trip. The sound had to travel down to the seafloor and then all the way back up. To find the actual depth from the boat, you must divide the total distance by 2. So the ocean floor in this example is exactly 1,500 meters deep. It's elegant, practical physics based entirely on how long it takes a vibration to return to its source. And that brings us to the end of our explainer today. We've charted the birth, the life, and the mathematical rules governing sound waves. But I want to leave you with one final thought. The human ear is biologically tuned to only hear frequencies between roughly 20 waves a second up to 20,000 waves a second. Our entire musical reality, every voice you have ever loved, exists strictly within that tiny, tiny window. So consider this. If we are entirely deaf to frequencies outside that range, what does the unseen universe of extreme, silent vibrations crashing through you right now actually sound like? Keep questioning, keep learning, and I will catch you on the next explainer.